Good afternoon, and a beautiful afternoon it is. I am Rebecca Bowling, and I am the director of the Drescher Center for the Humanities. And I'd like to welcome you to this 6th Humanities Forum event of the fall 2009 semester. This is the 4th of a 5-part series commemorating the 50th anniversary of the C.P. Snow's Two Cultures lecture. It was 50 years ago that the scientist-novelist C.P. Snow delivered his famous Reed Lecture at Cambridge University. Published as The Two Cultures and the Scientific Revolution, Snow identified a deep and dangerous divide between the sciences and the humanities. This series of lectures is intended to stimulate further discussion about the relationship between the sciences and the humanities, both here at UMBC, in academia, and society as a whole. The series is sponsored by UMBC's Drescher Center for the Humanities, the Human Context of Science and Technology program, and the Social Sciences Forum. Besides this afternoon's lecture by Professor and Provost Naomi Oreskes of the University of California, San Diego, next Monday, November 9th, we will host a faculty panel discussion on connections between the sciences and the humanities with Professor Tim Tobolewski, Professor of Mechanical Engineering, and Professor Manil Suri from the Department of Mathematics, both here at UMBC. We will also welcome back 2 former UMBC professors, Dr. Sue Dwyer, who is now Associate Professor of Philosophy at University of Maryland College Park, and Dr. Christoph Emscher, who is Professor of English at Indiana University. An entire list of the events that are part of the C.P. Snow series, as well as other departmental lectures that are part of this fall's Humanities Forum, are available on the table across from the elevator, so please be sure to take a copy. There's also copies of the Social Sciences Forum list, and remember, you can always go to our website, umbc.edu/Drescher Center. I just want to indicate briefly how opportune it is for us to have Dr. Oreskes here at UMBC as we explore the differences between the sciences and the humanities and the essential need to bridge these differences. Dr. Oreskes is not merely a geologist, but also a provost of the new 6th College at UC San Diego. Interdisciplinary examination of culture, art, and technology. According to its homepage, the 6th College makes use of its unique curriculum to prepare students to become effective global citizens who engage creatively and ethically with the complex issues facing the world in the 21st century. We here at UMBC like to think we are also preparing students to grapple with the problems of the 21st century, like global climate change. But we welcome the opportunity to have the provost of this unique college here to talk about global climate change and show us how she herself puts into practice an interdisciplinary examination of culture, art, and technology. Now I'd like to turn the program over to Dr. Joe Todorevich, the director of UMBC's Human Context of Science and Technology program, who will formally introduce our speaker.
Thank you very much, Rebecca, and thank you everybody for coming today. We're so very pleased to work together across a number of departmental and center and institutional lines over the last several months to put this on. And it's a great pleasure for me to welcome you to this consideration of the implications of C.P. Snow's Two Cultures. What we now see as Snow's somewhat simplistic optimism in science and technology began to take serious fire in the late 1960s, as many saw technology failing us in massive ways. Confidence in scientific theories, and even the social system of scientific practice, showed cracks as experts lined up on opposite sides of complex issues like air and water pollution, pesticides like DDT, and other issues of societal interest. But even in the sciences, the basic sciences, with little practical import apparent, things were in flux. The steady, familiar stars of the night sky were apparently arenas of unspeakable violence, where matter was ripped apart, sometimes flowed into mysterious black holes. But how all this happened was impenetrable, even to highly educated people. Shortly after Snow's book had appeared, physicist turned historian and philosopher Thomas Kuhn had proposed that changes in scientific theories had a lot more to do with social and cultural issues than most had believed. In place of steady accumulation of data, conservative tweaking of theories, he spoke in a language of paradigm shifts, ushering in revolutions. And right on cue, while scientists and philosophers of science hotly debated his theories and their implications, geologists took a dramatic U-turn and told us the solid earth beneath our feet was really drifting, that continents used to be somewhere else, and that they would in the future wind up elsewhere. In the late 60s, while cities burned and colleges were in turmoil, the most conservative of scientists, geologists, switched allegiances in a very short time and even resurrected a discredited minor figure from a footnote to a prescient hero. Naomi Oreskes, whom Rebecca has introduced with her post at UC San Diego, is exceptionally well prepared to talk to us today about crossing cultures of science and the humanities. She received a Bachelor of Science degree in mining geology from the Royal School of Mines of Imperial College, University of London, in 1981. She worked in the departments of geology, philosophy, and applied earth sciences at Stanford, taking the PhD in Graduate Special Program in Geological Research and History of Science in 1990. She held professorships at Dartmouth College and at New York University, joining the University of California, San Diego in 1998, where she eventually directed their science studies program and then was appointed provost of the 6th College. Professor Oreskes has won numerous grants, fellowships, and awards for a wide-ranging body of work that examines the practices of science, particularly proof and authority, and the place and operation of science and scientists in issues of national, indeed world, significance. The titles of her books say it well. The Rejection of Continental Drift, Theory and Method in American Earth Science from Oxford in 1999. She edited Plate Tectonics, an insider's history of the modern theory of the Earth with Homer Legrand in 2001. Her Science on a Mission, American Oceanography in the Cold War and Beyond is forthcoming. And most recently, Fighting Facts, how a handful of scientists had muddied the waters on environmental issues from tobacco to global warming, will be appearing with her collaborator Eric Conway recently. Among a host of more specialized professional articles and chapters, recent studies of hers have already entered the global climate change debate, from being used in Al Gore's An Inconvenient Truth to being debated in none less than Science magazine itself. It's a pleasure to welcome an old friend and colleague to us today. The title in the published program was Global Climate Change, Science, Polity, and Authority. Today's title is A New View of Science, title search Realism, which she has assured me are actually the same thing. So we look forward to hearing from you. Thank you so much for coming here today.
Well, thanks for that warm introduction. And when Joe was speaking about the Royal School of Mines, we used to joke when we were there that people would always get confused about what that was and say, you're going to the Royal School of Mimes? Or the Royal School of Minds, you know, and I said, well, that's good, you know, just keep people guessing because it's all related, whether it's mimes or minds or minds, you know, it's all about trying to figure out the way things go in the world, right? So my talk today is not explicitly about C.P. Snow, but as Professor Tatarovich just said, everything I've done really, in a sense, is related to C.P. Snow. Everything that I've done is about the two cultures. And as a historian of science, I think of myself as someone who is always working at the boundary between history and the humanities, that it is all about trying to understand science as a human and cultural activity. Science is something that we do, but that also affects us, that is part of culture but affects culture. And it's that dynamic between trying to understand the natural world, which we didn't make, or until now we didn't make, and the cultural world which we do make, and the interaction between them, that's really the heart and soul of history of science. And so everything I've done is really about that. So the talk is not explicitly about C.P. Snow, but it is about a set of issues involving science and culture, and C.P. Snow will make an appearance, I promise, towards the end of the talk. So my talk today is drawn from my new book, which actually has a new title. We didn't change it, our editor changed it. But the new title is called Merchants of Doubt. And as Professor Tatarovich said, the book is a study of a set of activities that have taken place over the last 40 years in which a group of scientists tried to challenge the scientific evidence of a set of environmental issues culminating in global warming. So in the book we examine this story, and that's what I'm going to talk to you about today. And so I want to just start by acknowledging my co-author on this project, Eric Conway, who's a historian of technology. He's the historian at the Jet Propulsion Laboratory in Pasadena, and so this work owes a great deal to him as well. So for the past long time, for nearly 20 years now, I suppose, I've really been focused on a number of issues in science, but they revolve around the questions of consensus and dissent in science. I've been particularly interested in the question of how scientists come to consensus on contested issues. Fairly recent has really focused on the epistemic dimension of that. That is to say, I've been very interested in the question of evidence. What is the evidence of global warming? How have scientists obtained that evidence? How have they evaluated it? How have they attempted to present it and communicate it to the public? And so when I've spoken on this topic, I've generally given talks that were crammed with facts. And I have this sort of incredibly brief history of the entire history of climate change, and often and it usually would begin with John Tyndall, the Irish experimentalist, who in the 1850s first established that carbon dioxide and water were greenhouse gases. That is, he defined what it meant for something to be a greenhouse gas, namely that it's highly transparent to visible light, but tends to be rather opaque to infrared radiation, and therefore can trap heat in the Earth's atmosphere, which is essential to life on Earth because Earth would be a very cold planet, much more like Mars or the Moon, if we didn't have water vapor and carbon dioxide in our atmosphere. So Tyndall understood the existence of greenhouse gases to be a good thing that made the Earth a congenial place for life. Now, in the early 1900s, Svante Arrhenius, the Swedish geochemist, was the first to suggest that carbon dioxide in our atmosphere might be increasing from burning fossil fuels, particularly from coal, and that this could in fact warm the Earth. He did the first calculations of the effects of doubling carbon dioxide on the atmosphere and predicted that if we doubled CO2 in the atmosphere, we would see a mean global temperature increase of between 1.5 and 4.5 degrees C. Now, Arrhenius was Swedish, so he thought global warming would be a good thing. Some people today still think that. The first person to suggest that it might be a bad thing was this man, Guy Stewart Calendar, a British engineer. And there's a wonderful new biography of Calendar by our colleague Jim Fleming that I definitely recommend to you. Calendar argued in the 1930s that the increase in atmospheric carbon dioxide was actually already detectable. And in an article in the Quarterly Journal of the Royal Meteorological Society, he suggested that temperature might be rising too. Now, in the 1930s, this was just an idea. The evidence for it was fairly thin at that time. Not very many people were particularly moved by Calendar's arguments. But the issue got picked up again in the 1950s by a number of people, one of whom was my late colleague in San Diego, Dave Keeling. In 1958, as part of the International Geophysical Year, Dave Keeling began the systematic measurement of carbon dioxide in the atmosphere. And one of the things that Keeling recognized, along with Roger Revelle and a number of other scientists at this time, was that the key scientific question regarding global warming at this time was what happens to the carbon dioxide that's released by burning fossil fuels? Because there's three places that carbon dioxide could go. It could go into the atmosphere and stay there, or it could be absorbed by the oceans, or it could be taken up by plants. So the hydrosphere, the atmosphere, or the biosphere. If most of the released carbon dioxide were taken up by plants or dissolved in the oceans, then the world would not warm. There'd be no increase in atmospheric carbon dioxide, and so global warming would not be a problem. Well, later on they started to worry about ocean acidification, but this is what Dave and Roger Revelle believed at this time. So it would be very important to actually measure carbon dioxide in the atmosphere to find out whether it was increasing or not. And so in 1958, Dave began the work that became known as the Keeling curve. It's easy for me to remember because I was born in 1958. So one day I was giving this talk and I thought, you know what, the Keeling curve and me were born in the same year. So I guess it's destiny that I'm doing this work. And the fact that Dave ended up being my colleague in San Diego as well. A lot of this work was done in San Diego, so it's been a great project for me to work on because I get to go to the archives and still be home for dinner. which the historians in the audience will appreciate. In any event, in 1958, Keeling began the systematic study of carbon dioxide in the atmosphere, and already by the mid to late 1960s, it was clear that although there's a great deal of daily variation, sorry, not daily, but annual variation associated with the difference between summer and winter, that there, in fact, is this working? Oh, there it is, yeah. Why am I not seeing it? Maybe my batteries are dying. But anyway, you can see that despite the annual variation, that there was a trend that was becoming apparent even already by the mid to late 1960s. So by 1965, Keeling was convinced that he had detected a trend, and of course we now know that this is in fact one of the best documented time series data in the history of earth science, showing a very, very clear, very consistent, and very systematic upward trend. And we would now say that the answer to the question that Keeling set out to answer in 1958 is that about half of all the CO2 that's released from burning fossil fuels ends up in the atmosphere where it's going to stay for a long time, and the remaining half is divided roughly equally between the oceans and the biosphere. So some of it is taken up by plants, that's an important part of the story, but enough of it stays in the atmosphere to be of concern. In 1958, this work got to the desk of President Lyndon Johnson, who declared in a special message to Congress, "This generation has altered the composition of the atmosphere on a global scale through a steady increase in carbon dioxide from the burning of fossil fuels." I take this quote to be important because it shows that it is possible to reach political leaders with scientific evidence, or at least it was possible back in the 1960s. And by the 1970s, there was in fact a consensus among scientific researchers that given the steady rise of CO2 that Keeling had demonstrated, that sooner or later global warming would occur. So when I talk about this historically, I like to say that it seems to me that historical evidence supports the idea that the consensus about global warming, well, is really a complicated thing because we have to ask, well, what exactly do we mean by global warming? But that the consensus of scientific evidence as it unfolded really came in two stages. And the first part was a consensus about a prediction. That is to say, scientists predicted that given the increase in CO2, we would expect to see global warming. And this was expressed by the US National Academy of Sciences in 1979 in a press release associated with a major report that came out at this time, in which they said, "A plethora of studies from diverse sources indicates a consensus that climate changes will result from man's combustion of fossil fuels and changes in land use." The land use is the plant part of the story. And I took this quote to be rather significant because some of you know there are some people who, now that it's pretty clear we do have a consensus that global warming has happened, there are some people, some skeptics who want to say, well, consensus, that's not how science works. Science isn't about consensus. But actually, I would argue that science is about consensus, and that's what the National Academy of Sciences thought too, that they made the point in 1979 that what science really is about the accumulated wisdom and expertise of the people doing the work. And already in 1979, this work indicated a consensus about a prediction, about something that we could expect to happen given what we knew was going on in the world. Now in 1979, the big question, and again this is why I say this consensus came in stages, the big question was when. When would this warming occur? And of course, if the answer was very far in the future, if it was 100 or 200 or 300 years away, then maybe we didn't need to worry about it. But if it were pretty soon, then maybe we did. Now most people at this time thought that the most likely answer was that global warming might begin to become detectable towards the end of the 20th century or the beginning of the 21st century. Other people thought no, later, more like the middle of the 21st century. One scientist I know who was on one of these early panels said that he was at a White House briefing where an official asked him, well, when is this all going to happen? So this is 1979, and one of the scientists on the panel says, well, we don't really know, but maybe in 40 years. And the official at the White House says, well, get back to me in 39. But the surprising answer that I think it's fair to say no one really did expect was that it was just a few years later. In 1988, climate modeler James Hansen declared in congressional testimony and also in a published paper in the Proceedings of the National Academy of Sciences that he was 99% certain that climate change due to increases in greenhouse gases was now detectable. Now, when Hansen made that declaration in 1988, a lot of his colleagues thought he was out on a limb, that he was probably going a bit too far. But very soon after that, the scientific community began to realize that Hansen, or began to feel, or to conclude that Hansen was probably correct. By the early 1990s, historical analysis, retrospective analysis of temperature records showed that a clear empirical signal was in fact emerging in the period sort of, can't see this from this angle, but from the somewhere around the mid-70s towards the 80s and into the early 90s, that a clear trend was beginning to show up. I think my battery's dying, but you can see it right here. But there's a fairly strong trend. So by the time we get to the late 80s, we've got something that does seem to be happening. And as a result of this analysis, plus additional evidence from satellites and ice core data, in 1995, the IPCC declared in its second assessment report that the balance of evidence suggests a discernible human impact on global climate. So this is what I would call the second stage of the consensus. The first stage of prediction that climate change is expected. The second stage of conclusion that in fact it's beginning to be detectable. And we talked in class today about, I interviewed Ben Sander, who was the lead author of the chapter on detection and attribution in this report, and he told me that they spent an entire day and long into the night at IPCC arguing about this word. So they actually had the sentence was written out with a blank, like that. The balance of evidence suggests a blank human impact on global climate, like a game show. They had to figure out what adjective fit in there, and they settled on discernible. That is to say, it could be discerned. And of course, this conclusion was based both on the empirical evidence, that is to say, the temperature records and the satellite data, but also on a well-established theoretical framework that linked the observed cause and effect. And of course, that's where the prediction piece of this is important. Scientists were able to make this prediction because they did, in fact, have a fairly robust understanding of the basic principles of radiative transfer in the atmosphere, despite a lot of complexities on the second and third order, despite a lot of details that many of which remain unclear even to this day. The basic picture of carbon dioxide as a greenhouse gas, along with methane, nitrous oxides, and other things, that has a strong impact on radiative transfer in the atmosphere, has been understood. Our level of understanding is very high because it's been understood for a long time, going back to Calendar and Arrhenius and even Tyndall. So this is sort of the nutshell version of what of my roadshow that I've been talking about around the country for about a couple of years now. But when I've spoken about these issues and presented this history to people, invariably there have been skeptics in the audience who have tried to raise questions or doubts about this story. And often they would raise certain sort of skeptical questions. For example, the most common question that I've gotten, and I get this from my students as well, is how do we know it's not the sun? How do we know that the observed warming isn't caused by the sun? And of course, one reason why I think it is important to understand the history is because if we just discovered global warming and we never had predicted it, it would be logical to look first at the sun, since the sun is the single most important dominant control on the climate of the planet. But of course, the history is important because we know that global warming was predicted because people understood that changes in carbon dioxide could cause changes in the climate. But nevertheless, that's not the most important reason for how we know it's not the sun. And so in the various talks that I've given, I've explained the different predictions between what you would expect to see if global warming was caused by greenhouse gases versus if it was caused by the sun. And of course, this was the key argument that was made in 1995 by the IPCC in the detection and attribution chapter. So the short answer to this is that if global warming were caused by the sun, we've got solar radiation coming in from the from outer space. If global warming is caused by the sun, we expect the whole atmosphere to warm up. But if global warming is caused by solar radiation hitting the Earth warms up, energy is re-radiated to space as infrared energy, that is to say heat, and that infrared is then trapped by greenhouse gases in the atmosphere, then we get a very different prediction. Then we predict that the troposphere, the lower half of the atmosphere, will warm up, but the stratosphere will actually stay the same or even cool as all of this heat is now being trapped in the lower atmosphere by by the greenhouse gases. And so this is a testable prediction. It can be tested by satellites in the atmosphere, which we have and have had for some time now. And these satellites have detected the temperature changes, the vertical structure of temperature changes in the atmosphere, and shown that, in fact, the troposphere is warming and the stratosphere is cooling. And there's no known way to explain that if this were being caused by the sun. So this is a really nice example of how science, at its best, can operate. You have a clear prediction. If it's the sun, it looks like this. If it's greenhouse gases, it looks like that. We can test it. We have tested it. We know this is what's going on. And for those of you who don't feel like you want to be bothered with details about the troposphere and the stratosphere, there's a great story about this that some of you may have known or heard about, the case of Massachusetts versus EPA that reached the Supreme Court about, I guess it's 2 years ago now, where EPA has wanted for some years now to regulate carbon dioxide as a pollutant on the basis that we know that it's causing global warming. And the Clean Air Act empowers the EPA to take steps to prevent air pollution that has an adverse effect on general welfare, including climate, which was in the Clean Air Act, which is, by the way, another digression. Did you ever ask yourself, why does the Clean Air Act mention climate? Right? Clean Air Act is from what? Anybody know? What year?
1977.
Right, early mid-70s, right? So obviously somebody knew something about the possibility of climate change from air pollution back in the 70s, right? And of course the answer is, well, we know that they did because of all this work. In any event, when this case reached the Supreme Court, because Massachusetts and 13 other states wanted the EPA to control global warming, there's a part in the transcript where Justice Scalia is asking questions, and he says something about the stratosphere, and the lawyers for the plaintiffs say, oh, excuse me, Your Honor, with all due respect, but actually it's the troposphere that we're talking about. And Judge Scalia responds, troposphere, stratosphere, that's why I hate these science cases. So it does matter, and if you remember nothing else from this talk, remember the difference between the troposphere and the stratosphere. This is how we know that global warming is not caused by the sun. Okay, but how do we know it's not caused by volcanoes? This is another question that I often get, and again, we have scientific evidence. Scientists are not stupid, they've thought about this question. We do know that volcanic eruptions can change the climate. This is very well documented historically. The giant eruptions of Tambora and Krakatoa, and then later Pinatubo, are known to have affected global climates. So we know that volcanoes can affect global climate, but volcanoes have a cooling effect in general, not a warming effect, because they mostly emit dust and sulfate aerosols that cool the climate. Volcanoes do emit some carbon dioxide, so we can ask the question, well, how do we know that the carbon dioxide in the volcanoes, carbon dioxide atmosphere doesn't come from volcanoes? And the answer here is stable isotopes that, you know that, everybody here knows what isotopes are, right? Yes, no? Okay, well, okay, so atoms of an element can have different isotopes, that is to say they have different masses, but they're the same atom, so like most people have heard of carbon-14, which is used for carbon-14 dating, so that's a radioactive isotope. It decays over time, so you can use it to figure out how old things are, but there are also things known as stable isotopes. So these are isotopes that have different masses, but they're not radioactive, they don't decay over time. And these are very, very useful scientifically because they can be used as fingerprints. Because it turns out that plants don't like heavy isotopes. Plants take up light isotopes much more readily than they take up heavy isotopes. And so plants tend to be depleted in carbon-13. They have very little carbon-13. So if you burn plants, or if you burn coal or oil or gas that are derived from plants or other biological stuff, you get carbon dioxide that is depleted in carbon-13. So if the carbon dioxide in our atmosphere was caused by greenhouse gases from the burning of fossil fuels, you should expect the carbon-13 value of the atmosphere to fall. And look at this diagram. This is one of my favorite diagrams in all of climate science. Here's the killing curve. Here's carbon dioxide going up, up, up. This is the killing curve now extended back. This is the modern carbon killing curve. This is data from ice cores. So here's what's going on with carbon dioxide in the atmosphere. You see it rising exponentially. And look at this. Here's the carbon-13 value. It's practically a mirror image. I mean, this is one of the nicest demonstrations of the source of a material in anything that I know of anywhere. Okay, so this is the story that I've been telling for the last couple of years. But one of the interesting things that has come up and that I began to notice as I was talking about this was how similar these questions always were. I would always get the same questions. And often they were presented actually not just as questions like, it's a legitimate question, I'm curious, how do we know it's not the sun? Totally legitimate question. But often in a very aggressive way, like, isn't it true that global warming is actually caused by the sun? So it had this sort of quality of, the sun did it, volcanoes did it. And often these people seemed to sort of know what they were talking about, but kind of in a slightly strange way. And as I said, often the question would begin, isn't it true that global warming could really be caused by the sun? Or isn't it true that global warming could really be caused by volcanoes? And so I started wondering, where were people getting all this skeptical misinformation from? Because it's one thing to ask an honest question about how do we know. That's great. I mean, I do that. I mean, this is what I want my students to ask all the time. It's another thing to sort of aggressively assert that the scientific conclusions of the IPCC are wrong because, in fact, the sun could have caused global warming. Okay, so an interesting piece of evidence that came out in 2007 relevant to this had to do with what Americans do or don't think about global warming. This is based on the work of Tony Lazarowitz at Yale. And in 1972, he showed that 72% of Americans were completely or mostly convinced that global warming was happening. So that seemed like pretty good news. Americans weren't too scientifically illiterate. But then the same poll also showed that 40% of Americans thought that scientists were still arguing. So this is in 2007, right? This is at the same time that the IPCC fourth assessment has come out, and this is 12 years after the second assessment report where scientists had essentially come to a consensus about the reality of global warming. And of course, in my own work, I had shown that scientists, in fact, did have a consensus on global warming and had had that consensus since the early 1990s. So I got interested in the question, why did so many people have the impression of a raging scientific debate when, in fact, the historical evidence did not support that conclusion at all? So the short answer, and this became the topic of our forthcoming book, is that we have this impression because it's the impression that a lot of people would like us to have. That over the past 20 years, a small but very powerful group of people, very influential, aided and abetted by well-funded think tanks and a compliant mass media, have wanted us to have this impression, have succeeded in giving us this impression. So this is the story we tell in our forthcoming book, which now has the title Merchants of Doubt. It will be released by Bloomsbury in the spring, so please buy it and read it. And it's the story of how a small group of scientists, not climate scientists, but actually physicists, exploited scientific uncertainty and promoted doubt about a set of environmental issues. And in the book, we explore why they did it, and it wasn't about money. So what I want to do now is just to give you an extremely brief summary of the book, extremely brief, and then to focus on the question that we address at the end of the book, which is why or how we, the public and the mass media, were taken in by these claims of scientific uncertainty. And the argument that Eric Conway and I make is that it's a complex question and it can't be entirely answered in a soundbite. But part of the answer, an important part of the answer, and it relates to the problem of the two cultures and how we view science, is that we have an incorrect view of science. And so I'll close my talk then by doing a brief reading from the book's conclusion. So the book tracks the story of a small handful of Cold War physicists, nuclear physicists and rocket scientists, the proverbial rocket scientists, who promoted the idea of doubt, that is to say scientific uncertainty, in order to delay regulatory action on a set of issues beginning with tobacco and culminating in global warming. So there are three principal players in the story and one think tank. The players are these three men. On the left is Robert Jastrow, a well-known astrophysicist who was very active in the 1960s in the space program, appeared on television many times discussing the Apollo program, and the head of the Goddard Institute for Space Studies. On the right, this man, William Nierenberg, a nuclear physicist by training who worked on the Manhattan Project and was the longtime director of the Scripps Institution of Oceanography in La Jolla. And in the center, Frederick Seitz, the president of the also a physicist, a solid-state physicist who had also worked on numerous weapons programs during World War II and in the Cold War, and then became president of the National Academy of Sciences in the 1960s, served as an ex officio member of the President's Science Advisory Committee, then became president of the Rockefeller University in New York City, and then worked as a consultant to the R.J. Reynolds Tobacco Company. The think tank in the story is the one that these three men founded. It's called the George C. Marshall Institute. It still exists today. And it was founded originally to defend Ronald Reagan's Strategic Defense Initiative against a scientist boycott of it. Between 1984 and 1989, Jastrow sites in Nuremberg worked to defend the Strategic Defense Initiative, better known as Star Wars, despite the opposition by the vast majority of academic physicists, computer scientists, and engineers, and instead to promote a rather alarming view of Soviet strength and American weakness that would justify the need for a ballistic missile defense system. Now, in the case of SDI, their major tactic was to cast doubt on the doubters. So scientists had argued that SDI was not technologically feasible. That is to say, they doubted whether it could ever be made to work. But Jastrow sites in Nuremberg insisted that it was not only feasible, but that it was necessary and, in fact, urgent. And they wrote numerous articles in which they made the case for Soviet superiority in technological and weapon systems, and saying that the United States was falling behind technologically. So one example is this article that Robert Jastrow published in the National Review in 1987, in which he insisted that if we did not act immediately to improve our nuclear capability, both offensive and also defensive with anti-ballistic missile defense systems, that the Soviets would overtake us and they would be able to dictate political terms in the Middle East, in Europe, wherever. And I love this. America has 5 years left. Now, at the time, Seitz was working as a consultant to the R.J. Reynolds Tobacco Corporation. And as many of you know, it has been written about by historians Robert Proctor, Alan Brandt, Stan Glantz, and others, the major strategy that the tobacco industry had settled on back in 1954, when the dangers of tobacco were first widely published, was to defend the product, to defend tobacco through doubt mongering. That is to say, to insist that the science was not really settled, that we didn't really know for sure if tobacco was dangerous, and therefore that it was premature to control tobacco use. In 1989, these two seemingly different strands merged. Seitz, Jastrow, and Nuremberg were working together in the defense of SDI, and then the Cold War ended. So, and these men were all fairly senior by this time. By this time, most of them were retired from what had originally been their position. So you might have thought that they would have been happy. They might have thought that we won the Cold War, that they had contributed to that success, and that they should feel proud of their accomplishments. But they didn't. Instead, they turned the attention of their institute to another matter. And that matter was what they called environmental extremism. That is to say, what they considered to be the exaggeration of threats, the insistence that government regulation was needed to control them, so they argued that the threats were exaggerated and therefore the demand for government regulation was also exaggerated. And they did this for a series of issues. First, acid rain, then the ozone hole, then the debate over secondhand smoke, and then finally global warming. And then later, another colleague who became involved sort of post hoc in a revisionist argument about the dangers of DDT, which some of us were discussing earlier. So this group of physicists denied the severity of all these problems, and in every case insisted that the science was too uncertain to justify government interference in the marketplace. So in the book we track each one, there's a chapter dealing with each one of these issues, and we show how in every case they use the exact same strategy. The science is uncertain, we don't really know, it would be very expensive to fix, and it would be foolish, it would be silly to spend all that money fixing it when we don't even know for sure if it's a problem. Now, Doubt is Our Product ran the infamous memo written by one tobacco industry executive in 1969, since it is the best means of competing with the body of fact that exists in the minds of the general public. So this particular memo has gotten a lot of attention from historians because it essentially encapsulates what the tobacco industry decided to do. And of course, this memo was a key piece of evidence in the case of the United States versus Philip Morris et al., in which the tobacco industry was found guilty of conspiracy and fraud under the RICO statutes for the efforts to defraud the American consumer on the health hazards of tobacco. So we know that. This has been very, very extensively documented because of that court case, which the tobacco industry lost and the US government won. But the same strategy was applied in these other cases as well. And of course, there's this very interesting connection in the person of Fred Seitz. In the book, we argue that if doubt was their product, scientists had to supply it. And part of what gave these claims credibility was the fact that there were scientists who were willing to supply the data. And so one of the things that Fred Seitz did in his work for the tobacco industry was to give the industry advice about areas in which he thought the science, where was the soft underbelly of the science, and also to fund scientific projects to cast doubt on the scientific evidence. So these men were involved in challenging the harms of tobacco both directly and also in the case over secondhand smoke. As I've already said, DDT, acid rain, the ozone hole, and the human causes of global warming. So now to know more about how they really did it, you'll have to read the book, or I would need 7 hours to talk, and I don't want to do that, and you don't. But, so what I want to talk about today, because I think this is in some ways the most important piece of the story. I mean, telling a story about bad people doing bad things, well, okay, we all know that that happens, These were not nice guys. But what I think is really interesting is why we fell for it. And by we, I mean we collectively, the American people, the mass media who repeated these claims over and over again. And in the book we show how the mass media did in fact repeatedly cite these claims. In fact, the New York Times only finally stopped quoting tobacco industry spokesmen on the hazards of tobacco in 1979, which is 14 years after the major Surgeon General's report that declared that cigarette smoking was hazardous to your health. And more than 25 years after the scientific community said that smoking was hazardous to your health. So why do we fall for it? Well, the argument we make in the book is because we have a wrong view of science. So at this point, I would like then to shift to the book and read to you from the conclusion of the book. Grab my water. So imagine a gigantic banquet. Hundreds of millions of people come to eat. They eat and drink to their heart's content, eating food that is better and more abundant than at the finest tables of ancient Athens or the palaces of medieval Europe. Then one day a man arrives wearing a dinner jacket. He says he is holding the bill. Not surprisingly, the diners are in shock. Some begin to deny that this is their bill. Others deny that there even is a bill. Still others deny that they partook of the meal. One diner suggests that the man is not really a waiter, but is only trying to get attention for himself or to raise money for his own private projects. Finally, the group concludes that if we simply ignore the waiter, he will go away. Well, I'm glad you're chuckling. That shows you get it. This is where we stand today on the subject of global warming. The past 150 years, industrial civilization has been dining on the energy stored in fossil fuels, and now the bill has come due. Yet, we have sat around the dinner table denying that it is our bill, and doubting the credibility of the man who delivered it. The great economist John Maynard Keynes famously said there's no such thing as a free lunch, and he was right. We have experienced prosperity unmatched in human history. We have feasted to our heart's content, but the lunch was not free. The bill includes acid rain in the ozone hole and the damage produced by DDT. These are the environmental bills of living the way citizens of the wealthy, developed nations have lived since the Industrial Revolution. Now we either have to pay the price, change the way we do business, or both. No wonder the merchants of doubt have been successful. They've permitted us to think that we could ignore the waiter while we haggled about the bill. The failure of the United States to act on global warming, as well as the long delays between when the science was settled and when we acted on tobacco, acid rain, and the ozone hole, are prima facie empirical evidence that doubt-mongering has worked. Decision theory helps to explain why. In their textbook, Understanding Scientific Reasoning, Ron Geary, John Bickel, and Robert Molden show that the outcome of a rational decision theory analysis is that if your knowledge is uncertain, then your best option is generally to do nothing. Doing something has costs, financial, temporal, or opportunity costs. And if you aren't confident that those costs will be repaid in future benefits, you're best off leaving things alone. Moreover, acting to prevent future harm generally means giving benefits in the present, certain benefits to be weighed against uncertain gains. If we didn't know that smoking was dangerous, but we did know that it gave us pleasure, then we would probably decide to smoke, as millions of Americans did before the 1960s. Uncertainty favors the status quo. As Geary and his colleagues put it, quote, "Is it any wonder that those who benefit the most from continuing to do nothing emphasize the controversy among scientists and the need for continued research?" To change the way the problem of global warming looks, Geary and his colleagues conclude, you would need, quote, "undeniable evidence both that doing nothing will lead to warming and that doing something could prevent it." The problem is, though, any evidence can be denied by parties sufficiently determined, and you can never prove anything about the future until it happens. You just have to wait and see. So the question becomes, why do we expect undeniable evidence in the first place? The protagonists of our story merchandised doubt because they realized, with or without the help of academic decision theory, that doubt-mongering works. And it works in part because we have an erroneous view of science. We think that science provides certainty, so if we lack certainty, we think our science must be faulty or incomplete. This view that science could provide certainty is an old one, but it was most clearly articulated by the late 19th century positivists who held out a dream of positive knowledge in the familiar sense of absolutely positively true. But if we have learned anything since the 19th century, it is that the positivist dream was exactly that, a dream. History shows us clearly that science does not provide certainty. It does not provide proof. It only provides the consensus of experts based on the organized accumulation and scrutiny of evidence. Throughout the debates that we describe in our book, contrarians insisted that journalists had an obligation to present both sides. Hearing, quote, "both sides of an issue" makes sense when debating politics in a two-party system, but there's a problem when the framework is applied to science. When a scientific question is unanswered, there may be 3, 4, or a dozen competing hypotheses, which are then investigated through research. Or there may be just one generally accepted working hypothesis, but with several important variations or differences in emphasis. In my book on continental drift, I explain how, when geologists were debating drift in the 1940s, Harvard professor Marlon Billings taught his students no less than 19 different possible explanations for the phenomenon that the theory of drift, later plate tectonics, was intended to explain. Research produces evidence, which in time may settle the question, as it did as continental drift evolved into plate tectonics, which became accepted theory in the 1970s. After that point, there are no sides. There is simply accepted scientific knowledge. There may still be questions that remain answered, of course, and this is what scientists then turn their attention to. But for the particular question that has been answered, do continents move or not, there is simply the consensus of expert opinion on that particular matter. That is what scientific knowledge is. Most of us don't really understand this. If we read an article in the newspaper presenting two opposing viewpoints, we assume both must have some validity, and we tend to think it would be wrong to shut one side down. But often one side is represented only by a single expert, or as we explain in our book, maybe 3. When it came to global warming, the views of Fred Seitz, Bill Nierenberg, and a handful of others were juxtaposed against the collective judgment of the entire IPCC, an organization that encompasses the work and views of thousands of climate scientists around the globe, men and women of diverse nationality, temperament, and political persuasion. And this leads to another important point, that modern science is a collective enterprise. For many of us, the word science does not actually conjure a vision of science. It conjures visions of scientists. We think of the great men of science, Galileo, Newton, Darwin, Einstein, and imagine them as heroic individuals, often misunderstood, who had to fight against conventional wisdom or institutions to gain appreciation for their radical new views. To be sure, brilliant individuals are an important part of the history of science. Men like Newton and Darwin deserve the place in history that they hold. But if you ask a historian, when did modern science begin, chances are she would not cite the birth of Galileo or Copernicus. Most likely, she would launch into a discussion of the origins of scientific institutions. From its earliest days, science has been associated with institutions. The Academia des Lincei, founded in 1609, the Royal Society in Britain, founded in 1660, the Académie des Sciences in France, founded in 1666. These institutions were created because the scholars of the day, savants, natural philosophers as they were variously called, until the 19th century invention of the word scientist, these scholars understood that to create new knowledge, they needed a means to test each other's claims. Medieval learning had largely focused on the study of ancient texts, the preservation of ancient wisdom, and the appreciation of texts of revelation. But later scholars began to feel that the world needed something more. One needed to make room for new information. But once one opened the door to the idea of new knowledge, then there was no limit to the claims that might be put forth. So one needed a mechanism to vet them. These were the institutional structures that we now take for granted in contemporary science: journals, conferences, and peer review, so that claims could be reported clearly and subject to rigorous scrutiny. Now, science has grown exponentially since the 1660s and changed in many ways, but the basic idea has remained the same, that scientific ideas must be supported by evidence, and that evidence must be subject to scrutiny and acceptance or rejection. The experiments can be experimental or observation. Sorry, the evidence could be experimental or observation. It can be a logical argument or a theoretical proof. But whatever that body of evidence is, both the idea and the evidence used to support it must be judged by a jury of one's scientific peers. And until a claim passes that judgment, that peer review, it is only that, just a claim. What counts as knowledge are the ideas that are accepted by the fellowship of experts, which is why members of these societies are often called fellows. And conversely, if a claim is rejected, the honest scientist is expected to accept that judgment and move on to other things. In science, you don't get to keep harping on a subject until your opponents just give up in exhaustion. And that's actually a reference to a comment earlier in the book where a colleague of Bill Nierenberg says, Bill was really brilliant, he was really interesting to talk to, but he would just never give up. And sometimes we just give up in exhaustion. You know? When you lose an argument in science, you don't get to press restart. Now, the he said, she said framework of modern journalism ignores this reality. We think that fair reporting must be balanced. We think that if someone disagrees, we should give him or her due consideration. We think it's only fair. But what we don't understand is that in many cases of scientific debate, that person has already received due consideration in the halls of science. When Robert Jastrow and his colleagues first took their claims to the halls of public opinion, rather than the halls of science, they were stepping outside the institutional protocols that for 400 years have tested the veracity of scientific claims. And indeed, many of the contrarian claims that we discuss in the book were duly reported by the media, including respected outlets like the New York Times and the Wall Street Journal. But very often these claims had already been discussed and considered in the halls of science and failed to pass the test of peer review. Or they'd been resolved, like the blaming the sun claim, that in fact scientists had looked at the influence of the sun on global warming and concluded that it wasn't the dominant cause of the observed warming in the last 50 years. So at this point, these claims can no longer really be considered scientific. And a fair scientist should at this point have moved on to other things. But these contrarians didn't. In a sense, they were poor losers. The umpires had made their call, but the contrarians refused to accept it. Moreover, in many cases, these contrarians did not even attempt to have their claims vetted. In fact, many of them had actually already stopped doing scientific research. And this is also an interesting part of the story, that these people we track are mostly doing this in their retirement years. Our story began in the 1970s when Fred Seitz was already retired from the Rockefeller University and working as a consultant to the tobacco industry, although he was a solid-state physicist, not a biologist, an oncologist, or a physician. The story continued in the 1980s when Seitz joined forces with Robert Jastrow and William Nierenberg. But how much original research on SDI, or acid rain, or the ozone hole, or secondhand smoke, or global warming did any of these men do? The answer is nearly none. A search of the Web of Science, an index of peer-reviewed scientific publications maintained by the Independent Institute for Scientific Information, shows that Frederick Seitz stopped doing original scientific research around 1970. After that, he continued to publish here and there, but mostly book reviews, editorials, and letters to editors, and a few works on great men in the history of science. Bill Nierenberg and Robert Jastrow similarly published very little in the peer-reviewed journals during this period. The fact is, these men were never really experts in the diverse issues to which they turned their attention in their golden years. They were physicists, not epidemiologists, ecologists, atmospheric chemists, or climate modelers. Indeed, to have truly been expert on all of the different topics on which they commented, they would have to have been all of these things: epidemiologist and ecologist, atmospheric chemist and climate modeler. No one in the modern world is all of these things. Modern science is far too specialized for that. To make the claims that pass the scrutiny of one's colleagues, one must be working at the cutting edge of a field. And this requires a degree of focus and dedication that makes it a daunting task just to be an expert in any one area of modern science, much less in several of them. If nothing else, this should have clued observers that these men simply could not have been real experts. An all-purpose expert is an oxymoron. Journalists were fooled by these men's stature, that they had had prominent positions in science. And of course, we're all fooled by the assumption that a smart person is smart about everything. Physicists have been consulted on everything from bee colony collapse to spelling reform and the prospects for world peace. And of course, smoking and cancer. But asking a physicist to comment on smoking and cancer is a bit like asking an Air Force captain to comment on the design of a submarine. He might know something about it, but then again, he might not. In any case, it's not his field. So what do we do? What do we do as citizens? We all have to make decisions every day, and we do so in the face of uncertainty. When we buy a car, when we buy a house, when we choose health insurance or save for our retirement, we make decisions and we don't allow uncertainty to paralyze us. But we may rely on people who we think can help. Normally, we try to make decisions based on the best information that we can get about the question. Let's say you need to buy a car. No doubt you will make some test drives, but probably you'll also talk to friends, especially those who know something about cars, and maybe read some magazines that evaluate cars, like Consumer Reports or Car and Driver. While you know that magazines make mistakes, and that prices and availability of options may vary, you assume that the information you find is reasonably accurate and realistic. Call it car and driver realism. But the metaphor isn't quite apt for our discussion, though, because in the end, buying a car is highly subjective, based to a large extent on questions of taste. I can decide what I think is the right car for me, but there is no experiment I can perform or observation I can make that will settle the question for others. There is, in the end, no truth of the matter about the right car to buy. So consider a different example. One of the largest financial decisions most of us will make in our lifetimes is the decision to buy a house. When we do, we consider numerous factors: the size and location, access to work, shopping and recreation, safety and security, the quality of local schools, and of course, the price. The process of deciding to make an offer on a house can be wrenching, involving, like the car, a host of subjective factors, but with far more at stake. Once we've made a decision to make an offer, however, we need to do one more thing. Something most of us give really rather little thought to, considering how much is at stake. We do a title search, or rather we hire someone to do a title search. We need to know that the title on the property actually belongs to the person who is selling it, or claims to be selling it, and that there are no outstanding claims or liens to stand in the way of our ownership. If the person we hire to do the search is incompetent or dishonest, we could end up in financial disaster. Yet we do trust the title search. Why? The short answer is because we don't have much choice. Someone has to do the title search, and we do not have the expertise to do it ourselves. We trust someone who is trained, licensed, and experienced to do it for us. We trust an expert. The sociologist Michael Smithson has pointed out that all social relations are trust relations. We trust other people to do things for us that we can't or don't want to do for ourselves. Even legal contracts involve a degree of trust because the person involved could always flee to Venezuela. If we don't trust others or don't want to relinquish control, we often can do things for ourselves. We can cook our own food, clean our own homes, do our own taxes, wash our own cars, even school our own children. But we cannot do our own science. So it comes to this. We must trust our scientific experts on matters of science because there isn't a workable alternative. And because scientists are not, in most cases, licensed, we need to pay attention to who the experts really are by asking questions about their credentials, their past and current research, the venues in which they are subjecting their claims to scrutiny, and, of course, the sources of financial support they are receiving. If the scientific community has been asked to judge a matter, as the National Academy of Sciences routinely is, or if they have self-organized to do so, as in the case of the Intergovernmental Panel on Climate Change, then it makes sense to take the results of their investigations very seriously. These are the title searches of modern science and public policy. It does not make sense to doubt them just because some expert, or some so-called expert somewhere, doesn't agree. And it especially does not make sense to dismiss the consensus of experts if the dissenter is superannuated, disgruntled, a habitual contrarian, in the pay of a group with an obvious ideological agenda or vested political economic interest, or in some cases, all of the above. Sensible decision-making involves acting on the information we have, even while accepting that it may well be imperfect and our decisions may need to be revisited and revised in light of new information. For even if modern science does not give us certainty, does not give us proof, it does have a robust track record. We have sent men to the moon, cured diseases, figured out the internal composition of the earth, invented new materials, and built machines to do much of our work for us, all on the basis of modern scientific knowledge and insight. While these practical accomplishments do not prove that our scientific knowledge is true, they do suggest that modern science gives us a pretty decent basis for action. In the early 1960s, one of the world's leading epidemiologists, Bradford Hill, who was initially skeptical of the idea that tobacco was deadly, came around to accepting that the weight of evidence showed that indeed it was. In response to those colleagues who still doubted it and insisted that still more data were needed, he replied, quote, "All scientific work is incomplete, whether it be observational or experimental. All scientific work is liable to be upset or modified by advancing knowledge. That does not confer upon us a freedom to ignore the knowledge we already have, to postpone action that it appears to demand at a given time. Who knows," asked Robert Browning, "but the world may end tonight. True, but on available evidence, most of us make ready to commute on the 8:30 the next day." Now, don't get us wrong. Scientists have no special purchase on moral or ethical decisions, and a climate scientist is no more qualified to comment on healthcare reform than a physicist is to judge the causes of bee colony collapse. The very features that create expertise in a specialized domain lead to ignorance in others. So our trust needs to be circumscribed and focused. It needs to be very, very particular. Blind trust will get us into at least as much trouble as no trust at all. But without some degree of trust in our designated experts, the men and women who have dedicated their lives to sorting out tough questions about the natural world we live in, without some degree of trust, we are paralyzed, in effect not knowing whether to make ready for the morning commute or not. We are left, as Alexis de Tocqueville recognized 200 years ago, with nothing but confused clamor. Or as Shakespeare suggested more than 200 years before that, life is reduced to a tale told by an idiot, all sound and fury, signifying nothing. C.P. Snow once argued that foolish faith in authority is the enemy of truth, but so is a foolish cynicism. In writing this book, Eric Conway and I plowed through hundreds of thousands of pages of documents, and as historians during the course of our careers, we have plowed through millions more. And often we find that in the end it is best to let the witnesses to events speak for themselves. Excuse me. So I'd like to close with the comments of one tobacco industry executive who in 1976 grasped quite clearly what was going on in his industry. And he said, quote, "A demand for scientific proof is always a formula for inaction and delay, and usually the first reaction of the guilty. The proper basis for such decisions is, of course, quite simply that which is reasonable in the circumstances." We agree, and we hope it's not too late. Thank you very much. Sure, of course.
Yes.
I have a question for Correct me if I'm wrong, but I I learned that the planet Earth lives a circle or a cycle of that alternates between warm periods and ice ages. Where are we right now? Are we accelerating a normal process, or are we adding something odd to the process?
Well, I mean, in a way, it's a matter of definition of terms. But you're right. The Earth's climate has a very enormous amount in history, and we actually live today in the Ice Age. I mean, geologists would say that we're in the Ice Age, and that we live right now in an interglacial period. So we live in a warm period, and that ended, the cold period. The last cold period ended about 12,000 years ago. So the natural cycles are complex, but most Earth scientists would say we live in a warm interglacial period, and therefore the natural cycle, what we would expect to happen, other things being equal, is that we would in fact begin to be moving into the next ice age. That 6,000 to 10,000 years from now, we would expect to move into another glacial period. What's happened, though, is that global warming through greenhouse gases and land use changes has actually reversed that natural trend. So we might expect to see some degree of cooling, and in fact, I mean, some people have made a big fuss about this. Back in the 70s, there were some scientists who did predict that we should be starting a cooling trend. But what's happened is that whatever natural cooling trend may or may not have started, that has been overwhelmed by the warming trend caused by greenhouse gases. So in effect, you could say we've reversed the natural cycle and moved ourselves into a warming trend where we would have expected, if anything, to have been moving in the direction of cooling.
Other questions?
I'm familiar with some parts of the world where we're starting to see snow and ice where there wouldn't normally be any. How does that relate to what you're talking about?
Okay, I'm not sure which particular parts of the world you're
Well, it
thinking
was
about.
Karachi, the city of Karachi, yeah.
Understand.
And I think 2 years ago or last year, there was snow there, and
Which
that
is quite irregular, yeah.
Right.
Well, I mean, one reason why scientists like to talk about climate change rather than global warming is because they feel that, in fact, that's a better way of describing the phenomenon. Because the climate change that's produced by increased greenhouse gases is not all warming. It's a set of changes and disruptions to the climate that are expected to lead and have already led to a net warming of the planet as a whole. But how that warming gets distributed is very complicated. And so one of the things that climate models predict is that with warming, you expect many areas of the world to get hotter and drier. So for example, the American Midwest is expected to get much hotter. But it turns out, even though it's going to get hotter, the climate models cannot actually predict if it's going to get wetter or drier. Because it can be that with more heat, things get drier because you have more droughts. But it's also possible that more heat causes the air to be able to carry more moisture across the continent, and you could actually end up with wetter conditions. And the same is true for cooling. There are some areas of the globe where global warming could in fact cause cooling, and the area where that's thought to be best understood, although it's not well understood, is actually Europe because of the Gulf Stream. And this was the scenario that was played out in a much exaggerated form in the film The Day After Tomorrow. So we know that Europe, if you think about, London is the same latitude as Labrador. So if it were not for the Gulf Stream, the whole United Kingdom would be under snow and ice much of the year. But Northern Europe has a relatively temperate climate because of the Gulf Stream, which brings relatively warm air masses from the Caribbean into Northern Europe. So Madrid is the same latitude as New York, but Madrid is much warmer. Some people believe that global warming could change the flow of the Gulf Stream in a way that could damage that warming effect, and so that Europe could end up becoming much, much colder. So the net impact of global warming, even though the Earth as a whole has warmed up, some areas could in fact become much colder. And of course, this is one of the reasons why the whole thing is alarming, because the consequences of changing the heat balance in the atmosphere are very great, but they're not well understood. And so on the one hand, scientists are confident in saying, yes, there's been global warming, and yes, we expect more. But on the other hand, scientists are not confident about predicting what that means for specific places on Earth. And that's very serious in terms of planning, because of course, if we knew for sure exactly how global warming would play out in all the different places on the globe, we might say, okay, we can plan for this, the time has come to mobilize our technological ingenuity and plan for the future, which we need to do anyway, because there will be some global warming no matter what we do tomorrow. But it's very, very difficult because of these complexities that are not well understood. Yeah, I think you're
what would have attracted the physicists to such diverse fields as like the Star Wars program and then tobacco global warming. Were they affiliated financially or just political ideology?
Right. So I don't talk about that in this talk because it's hard to talk about that in a subtle and nuanced way. And so this is my pitch for buying and reading the book. So I'll get you excited then to find out. But the short answer is that it's really ideologically driven. It's not about money. They're not doing it. They're not in the pay of the fossil fuel industry, although their institute does get support from foundations that are themselves supported by certain corporations. But it's really ideological. It's really about a kind of free market ideology that's tied to their Cold War anti-communism. So these men all believe that by helping to develop weapons programs and weapons delivery systems during the Cold War, that they had kept America safe from communism. And so this is why 1989 is such an interesting year, that this is the year that the Cold War ends, the Berlin Wall falls, and it's the year that they begin to attack environmentalists. And there's one really wonderful place in the story where they refer to environmentalists as watermelons, green on the outside, red on the inside. So that's kind of the short version of it, right? That they see environmentalism as a kind of slippery slope to socialism, and that if the government intervenes to control global warming, then then what else will they want to control as well? And this is why they get involved with the tobacco industry. That they essentially accept the tobacco industry argument. The tobacco industry always argued that it's up to people to decide for themselves. This is a free world, and if you have a habit that you enjoy that's dangerous, you have a right as a grown-up to make that decision, and it's not for the government to intervene. Now, the contrary argument, of course, is, well, yeah, that would be true if the product were safe, right? But we do have laws that make it illegal to sell dangerous products, right? So if it's dangerous, then that whole equation gets kind of altered. And so this is why the tobacco industry insisted that it wasn't dangerous, that we didn't really know for sure if it was dangerous. Now, they lost that argument up to a point in the 1960s, but only up to a point, because there were people in the 1960s who thought that tobacco should be outlawed, that it should be banned entirely, it should be criminalized like heroin, that it's an extremely dangerous drug. There was already evidence that nicotine was addictive, and so it should become a controlled substance. The tobacco industry, in a sense, won, because that didn't happen, right? What did happen was simply we got warning labels in the package that said this is dangerous, right? So that was kind of the compromise that was worked out in the 1960s. The debate gets reopened in the 1990s, and it gets reopened in an even more furious way. The documentary material from the 1990s is much more emphatic, much more vigorous, and much more angry than the materials from the 60s, because the scientific evidence now demonstrates that secondhand smoke can kill you. And that, of course, completely undermines the tobacco industry argument. Because it's one thing for me as a grown-up to say, look, I'm willing to take this chance. I go rock climbing, I've flown in helicopters, and if I want to smoke cigarettes, it's my decision, right? That's one kind of an argument. But to say that I have a right to do something that will kill my neighbor or my children, and this was the part of the scientific evidence that the tobacco industry got most upset about, that the big studies in the early 90s showed very clearly that secondhand smoke increased bronchitis and asthma in infants and children, and that there were higher mortality rates among children of parents who smoked. That's a whole different kind of argument. And then saying, well, we're grown-ups making free choices in a free society, that doesn't work if you're killing your babies, right? So.
Well, she more or less answered my question, but just to follow that argument just a bit further, the people that are facing climate change also have children and grandchildren.
Right. But they believed, and I think honestly, I think that this was an honest conviction, that the risks of totalitarianism were greater than the risks of global warming. That'd be a short version of their argument.
Sorry. Yeah.
So
Dangerous,
what
dangerous.
Svante Arrhenius was here today and brought forth his argument again that global warming is good. How would you respond to that? Where's the evidence that global warming is going to be worse than what we would have today?
Well, okay. I think there's two things about it. And again, this is where I'm freely announce the limits of my expertise. But I'm a historian of science. I think if you're concerned about that question, I would refer you to the IPCC, Working Group 2, which is all about the impacts of global warming. But I think that the short answer to it, having read those reports, is the short answer is sea level rise. Because hundreds of millions of people live within a meter of sea level. And the scientific evidence is very strong now that if we don't do something to slow down global warming very quickly, we are looking at, well, the last IPCC report gave a minimum estimate, completely leaving out Greenland and Antarctica, of 70 centimeters of sea level rise. So essentially, 3/4 of a meter of sea level rise. If you add in the Antarctic and Greenland component, well, that's poorly understood, but I think most scientists would say that it's extremely likely we're looking at least 1 meter of sea level rise from global warming, and possibly a lot more. Possibly, well, as much as 5 meters in the kind of worst case scenario, but say between 1 and 5 meters is sort of what the range of physically plausible estimates look like. That means the dislocation of hundreds of millions of people. It means the drowning of major cities all over the planet. So this is a huge social, political, and economic consequence. The Stern report that was commissioned by the British government about 1.5 years ago, led by Nicholas Stern, who's the former chief economist of the World Bank. So we're not talking about a member of Greenpeace, right? We're talking about one of the world's most distinguished economists who did calculations of what that means financially, let alone what it means culturally and in terms of human suffering. And it's looking at many, many trillions of dollars. So these are very, very profound impacts. And the idea that this is something minor, something small, something that we could just get used to, I don't believe that the scientific evidence is consistent with that view.
Yes. If you'd stand.
Okay. My question would be, what is the present day situation? Are there follow-ups to this George C. Marshall Institute, or do they still do their business? Is it some other people?
Yeah.
I know some names, that's why I'm asking.
Yeah,
I'm just
I mean,
curious.
it hasn't ended. We had to finish our book, so we kind of cut it off at a certain point, which was the 2007 IPCC report, but it's still going on. And if you want an example, this book, the Freakonomics guys who have just come out with another book, I mean, they have a whole thing where they're basically saying, oh, no big deal, we can just fix global warming with geoengineering, throw a little sulfate in the atmosphere and everything will be fine. So yeah, it's still going on, and I think it's going to continue to go on for some period to come because a lot is at stake. And there will be winners as well as losers. There's money to be made on this. I mean, there's a very interesting split going on in the business community now. In my home state in California, our governor has been one of the leaders of the Western Governors Climate Coalition, and California has essentially agreed to Kyoto-level reductions in carbon dioxide. Of course, the big question is how we're going to do that, but if the state economy collapses, we may be able to do it very easily. But hopefully that won't be the way we do it. But one of the very interesting things is that when this bill was being debated in California, it split the business community. And the Chamber of Commerce, who represents what we could call traditional American business, was very, very strongly opposed to it and published advertisements and things against it. But the leading organization of Silicon Valley executives and venture capitalists supported it because, of course, they believe that there are great opportunities in green technology, green IT, that people who figure out how to make more efficient photovoltaics, people who figure out how to make a better transportation system, information systems. IBM is already starting to talk about, smart grids. There are a lot of opportunities for technological innovation here. So there are many business opportunities, and it's interesting to see how that political debate is beginning to shift. But nevertheless, you do have, certain corporate interests, certain traditional groups represented. There was a piece in the Wall Street Journal about this just a couple of days ago about how the Chamber of Commerce, is opposing all of the climate bills that are on the Hill right now, all of them. So, I think this story is not yet over, that's for sure.
Yes.
I'm curious. You mentioned that the three men involved with promoting denial work, things such as tobacco, DDT, and et cetera, they were nuclear physicists. So, to put it in non-technical terms, the main thing these guys were concerned with was with the quickest way to turn Moscow or Leningrad into a nuclear slag pile before the Soviets could do the same thing to Washington or New York. Why then do you think, knowing what their background was, the public was so inclined to believe the doubts they were casting about things that weren't in their field, especially, with respect to climate change, DDT, and especially tobacco?
Right. Well, I think because the public didn't really know who they really were. So they would be quoted, we did a search of the New York Times Index. These guys were quoted scores and scores of times in the New York Times, and they were often just quoted as, a leading scientist or a scientist with the Marshall Institute, or Seitz, whenever he would speak, he would always make a big point about having been a president of the Academy. So he would say, so the New York Times would say, well, Frederick Seitz, a former president of the National Academy of Sciences. So this sounds really credible, right? But of course the question, so this is part of my argument, right, is it's not enough just to be a scientist, right? We have to dig a little deeper, right? And we need to ask, well, what kind of a scientist are you? What are you working on now? That's probably the single most important question that a citizen or a journalist could ask is, what are you working on now? Because if a person isn't actually working on the topic and keeping up with the literature, then I think there's really a serious question about whether or not they can plausibly be considered an expert.
Last question, maybe.
One more after you.
Yeah, in your research, did you figure out why there's a beginning lack of confidence in the scientific theory itself? Just like why people are able to cast doubt on scientific theories that are given to them?
Well, I don't think you really have to cast doubt initially. We were talking about this earlier today. Science is intrinsically conservative in the following sense, that in science you start wherever you are with the body of knowledge that's already been established. And the assumption in science is that the knowledge you inherit is correct, unless somebody shows otherwise. So if someone comes along with a new theory, a new idea, or a claim that what we used to think was true is wrong, the burden of proof is on that person. So there's a pretty high bar to establish a new theory in science. And I think you see this in the history of continental drift and plate tectonics. It takes a lot to establish a new scientific theory. And the more profound the theory is, the more different things it impacts, or the more radical it is, the higher that bar is. So when continental drift was being debated in the 1920s, some scientists said, look, this is a really radical theory, so we have a right to set the bar higher than we would for just something kind of a modest change. And that made Alfred Wegener very annoyed. But I think in a way it was legitimate, right? If a theory is really radical, then we have a right to expect a very high degree of evidence for it. So in the case of global warming, it's not so much that the theory itself was radical. In a sense, the theory is actually very conservative. The first order effect is basic physics that goes back to the 19th century. But it's radical in its implications. Because if it's true, it means that the whole way our economy, this is the argument at the end of the book, right? The whole way we've built our economy, the prosperity that we enjoy, that most of us would accept as a good thing, it's like there's this fatal flaw, Did I do that? Time right off.
Interesting, though.
Yeah. So behind the screen is the soft underbelly of Western civilization, right? So it's kind of like that. It's sort of like saying, when we discovered that we could tap fossil fuels, that was a fantastic discovery, right? And great things were done with that. But now we discover, oh, there's this dark side, there's this soft underbelly. So in a way, it's like a Greek tragedy, right? You have the hero with the fatal flaw. So the fatal flaw of fossil fuels is greenhouse gas emissions, right? And that's a tough nut to swallow.
I think one more question, and then we'll give you a
Okay.
we'll have a
I
reception.
was wondering, you keep referring to the general reference to the physicists that are promoting doubt as being scientists, but wouldn't you say that is, you see that in literature which is promoting, education about global warming? As being, like the fact that, or the idea that there's a scientific consensus, or the idea that scientists believe this. And so you have, even in the literature promoting or the idea of global warming, you have the general notion of scientists, and you don't have the specifics.
Yeah, right, that's a good point, right. So I would say that that's kind of, in a way, a mistake. But what we really should say is, first of all, we should say climate scientists say this, right? But it is important to make that distinction. Who's speaking here, right? So when the IPCC speaks, that's the voice of the thousands of climate scientists, climate researchers who participate in that process. And I think that is an important distinction. The other part of it, of course, is it isn't enough to just say scientists say, right? The next question is, okay, what is that based on? And that's where I think it just is extremely important as citizens, journalists, whoever we are, to ask what the evidential basis is. So when these guys said, well, we don't really know enough, or it's just the sun, the follow-up question to, oh, it's just the sun is, well, what's that claim based on? Where is the evidence that shows that this can all be explained by the sun? And then the answer is, well, there isn't any, right? But it's that lack of the follow-up question that I think has gotten so many of us into trouble.
Please join us for reception afterwards, and let's continue the conversation.